Hello, welcome to lecture number 13 of the Quantum Mechanics and Molecular Spectroscopy course. Okay. We will quickly go through the contents of lecture number 12 before we proceed with lecture number 13. In the last class, I told that a charged particle, when placed in electromagnetic radiation or the light, will experience what is known as Lorentz force. Okay, and Lorentz force F L is equal to Q times E plus Vb. Okay, where Q is the charge of the particle, so this is the Lorentz force. Okay, where Q is the charge of the particle and E is the electric field, B is the magnetic field, and U is the velocity of the particle, or V is the velocity. And this, in terms of classical mechanics, force is given as mass into acceleration, which could be written as d by dt of momentum. Okay. So, we use the analogy of this and converted the momentum p or p prime is equal to p minus qa, where p is the original momentum and A is the vector field. Okay. Having done this, then we cast the total Hamiltonian H as p square p prime square by 2m plus v of x. We considered only in the vx direction, and after doing the necessary math, okay, we came across the equation in which H prime of t is given by I h bar q by m a del. Okay, that is your okay, but minus I h bar del is nothing but operator p. Okay, okay. Then we could condense this equation to finally, okay, H prime of t is equal to minus q e naught by omega m cos omega t E dot p. Okay. So, this could be written as minus q by plus, there was a plus omega m cos omega t, and you know E naught into E p, and this E naught into E written can be written as E. So, q by omega m cos omega naught E dot p. So, this is H prime of t. Okay. But in the case of particles which are an atom or a molecule which has large number of particles, so which all of the charged particles will interact with the light. So, this H prime t for this is for one charge, and when for collection of charge this will turn out to be minus plus E naught by omega m cos omega t sigma over n, okay, q n m n, sorry, this is not needed because m exchange going to be different for different particles, m n p n, okay, because p is going to be momentum of the associated particle. So, this is for collection of charges. Okay. So, we will start this lecture with this equation. So, what we have at the end of the last class, we had this h prime of t equals to E naught by omega cos omega t sigma over n q n m n epsilon p, okay, where q n comma m n comma p n are charge, mass, momentum of the nth particle. Okay. So, this is what we have. Now, if you go back to the coefficient or the probability, okay, your P of t, that is the probability of f, okay, is equal to 1 over h bar square integral or modulus of integral 0 to t prime e to the power of minus I omega I f t integral f h prime of t I dt modulus square. Okay. That means we still have to evaluate this integral f h prime of t I. So, unless this integral is evaluated, of course, you cannot evaluate this p of t. Okay. Now, to evaluate this integral, now we know the Hamiltonian. So, we need to plug in this value of h prime of t. Okay. So, your integral f h prime of t I is given by f E naught by omega cos omega t sigma over n q n m n epsilon p n. So, this is the integral that I need to evaluate. Okay. Now, I am going to slightly rewrite this equation or this integral. F h prime of t I equals to, okay. Now, E naught by omega cos omega t, I will take it outside, integral f, because E naught is a constant, omega is a constant, cos omega t is a constant as far as this integral is concerned, f, because f and I are the eigenfunction of the time independent Hamiltonian. Okay. F times sigma over n q n by m n epsilon p n. Okay. Now, to begin with, we will start with a slightly some other equation. So, if I take a quantity called R H naught commutator, that is the commutator of of operators R and H naught. Okay. Right. Now, this can be evaluated at this commutator R comma H naught can be evaluated to be IH bar P by M. Okay. Now, I am going to take a small detour and try to evaluate this commutator, but always remember the commuters are evaluated with respect to some function. So, if there is an R operator and there is a H naught operator, okay, H naught is along the direction of R, so this will be equal to minus H bar square by 2m d square by dr square with some potential V of R, okay, that your H naught. Okay. Now, then all of this will act on a function f of R. So, let us evaluate the commutator. So, by the way, this is okay, this is also called minus H bar square by 2m del R square plus V of R. Okay. So, now what you have to evaluate? You have to evaluate R H naught commutator with respect to f of R function. Okay. So, this will be equal to R times, okay, minus H bar square by 2m del square f of R minus H bar square by 2m del square R f of R. Okay. Now, take the first term. So, that is going to be minus H bar square by 2m because it is constant R time del square f of R. Okay. Now, the second one is this is minus of this minus, so this will be plus H bar square by 2m del square R f R. Okay. Now, if you take this, I am just going to evaluate this. So, del square R f of R, this is equal to, but del is nothing but del square. So, that is nothing but del of del R f of R. So, one can first evaluate this. So, this is nothing but del times, now this is a differential, del is nothing but d by dr. So, you have a differential function. So, first acts on R, so it will give you 1, so you will get f of R. Okay. Now, second, this will act on del f of R. Okay. So, what you will get is plus R times del f of R. Now, again, now this del the second del acts on it, or the second differential acts on it. So, you will get del f of R plus, now you have again a function. So, this is one function and this is another function, del of R is 1. Okay. Okay. So, you will get del f of R because that is 1 plus del acting on del f of R give me R into del square f of R. Okay. So, now I am going to plug this in here, and what you will get is, so what I am evaluating? I am evaluating R H naught commutator. So, this is equal to minus H bar square by 2m R del square f of R plus H bar square by 2m. Now, what you have? Del FR, the 2 del FR 2 del Fr plus this is R square R del square Fr, R del square F of R. Now if I expand this, this will be minus h bar square by 2m R square R del square F of R plus this 2 and this 2 will get h bar square by 2m del Fr, okay, plus h bar square by 2m R del square Fr. Now, we will see that this m and this 10 will get cancelled, though, so this will be equal to h bar square by 2m del Fr. So, this is nothing but this is equal to minus I h bar, so there is no 2 here, m here, just m, by m multiplied by I h, sorry, this is plus I minus I h bar by, so minus I square minus 1 into minus plus I h bar del F of R. Sorry, finally you do not have F of R because it is evaluated with respect to F of R. So, then you have to put F of R here as well. So, then your R, but this is nothing but P of R. Okay. So, what you get R H naught commutator will be equal to I h bar by m P. Okay. So, because now I want to use this P operator here. Okay. So, let us continue. So, what was the equation that we had? This one. Okay. So, F h prime of T I equals to E naught by omega cos omega t acting on F sigma over n q n by m n p n I, and we found that R h naught, sorry, commutator is equal to I h bar P by m. Okay. Now, what I am going to do this, so I am going to plug in here. So, this will be equal to, so this will now be equal to E naught by omega cos omega t F sigma over n q n, okay, into p n by m n. Okay. So, P n by m n, okay, is I. So, this is nothing but E naught by omega cos omega t. So, I h go on the other side, that will be I will become minus I and h. So, you have h bar minus I, that is what you get. Okay. Sigma or F epsilon F sigma or n q n epsilon n r n h naught. Okay. So, that is the new Hamiltonian when you have plugged in this value. So, this will be equal to, So this will be equal to minus I E naught by h bar omega cos omega t omega t into f. Okay. Now let us expand this commutator. So this will be sigma over n, okay, q n r n h naught minus q n h naught r n I. Okay, I have just expanded this commutator r n h naught because then it will be r n h naught minus h naught r n. So this will be equal to minus I E naught by h bar omega cos omega t. Okay, I will write it as two because there are two terms here. I can write it as two separate integrals. So f of, okay, sigma over n q n r n, okay, because r is just a okay. Now epsilon h naught acting on I minus f sigma over n q n h naught epsilon r n I. Okay. So now this h naught will act on I on give me E I, okay, I. So this will now be equal to I E naught by h bar omega cos omega t. This h naught acting on I give me E I. So E I, okay, f, because E I is a number, f sigma over n q n r n epsilon, okay, I. Now this h naught will act on the other side because you know h naught is a Hermitian operator and we know the turnover rule. So if I use turnover rule, this h naught can act on f and give me EF, okay, complex conjugate of it, but energies are always real. So complex conjugate of EF star will be only EF. So this will be minus EF integral f sigma over n q n r n. Now we will see the integral in both cases is the same. So essentially your f h prime of t I can be written as minus E naught I by h bar omega cos omega t into E I minus E f into integral f sigma over n q n r n epsilon divided by I. Okay. Now what is EIFI? EI minus FI, EF, sorry, EI is equal to delta E IF. So this is nothing but H cross omega IF. So this is nothing but this is equal to minus I E naught H cross omega cos omega t. This will be H bar omega IF integral f sigma over n Qn Rn epsilon I. Okay. Now this H bar omega and this H bar shall get cancelled. So what you will get is this minus I E naught cos omega t omega IF by omega. So this is very important term. Okay, remember. Okay, and f sigma over n Qn Rn I. Now, for if there are charges like this distributed over some this one, okay. So this is charge Q1, this is charge Q2, this is charge Q3, Q4, Q5, etc., Q6, Q7, Q8, Q9, Q10. This is my center, Q11, and then you have radiuses R1, R2, R3, R4, R6, R11, R10, etc. So what is this? If I take, so this is a product of Q and Rn, sum over. Okay, if you have charges distributed like that, that will give you the dipole moment. So for n charges, sigma over n Qn Rn should be equal to mu. That's a dipole moment of the molecule. Okay, so that is nothing but is equal to minus I E naught cos omega t omega IF by omega f mu epsilon I. Okay. Now, what is mu dot or mu epsilon? Mu epsilon simply means that the mu has to have a dot product with along to the epsilon, that is the electric field vector. Okay. So that will give me is given by this equation. Now one could understand, okay, if you forget these prefactors, this integral depends on the dipole moment of the atom or the molecule. Okay. By the way, dipole moment of atom I don't know, because its dipole moment, its permanent dipole moment is 0, but dipole moment is not permanent dipole moment. You must understand mu is not equal to mu naught. We will come to that at later sometime, but essentially the initial and final states will couple, okay, with respect to the projection of the dipole moment along the electric field vector. So this is nothing but the projection of dipole moment along the electric field vector. Okay, and the projection of the dipole moment along the electric field vector determines the selection rules, and this will lead to selection rules. Okay, we will stop it here for this class and continue in the next lecture.